Okay, so today we're going to start looking more at the graphs of functions. Remember, yesterday we talked about how to determine whether it actually is a function, whether each input has exactly one output. We talked about domain, range a little bit, domain a little more specific. Today, like I said, we're going to start taking a look at the graphs. So, you should be able to generate the graph of any function just by, of course, plotting some points, making a t-chart, doing the calculations, being able to graph it by hand. So that's what I'm going to start off with. Of course, we know how to generate graphs in our graphing calculator, but we're going to talk about sometimes the viewing window isn't maybe necessarily the best on the 10 by 10, so how to change that. We evaluated piecewise functions yesterday. Today I'm going to show you how to do the graphs for those. Vertical line test, you know vertical line test. We've been doing that since 8th grade math, but we'll talk about that. And then of course how to figure out whether an equation represents a function. So let's start by graphing, by plotting points. We're going to start with what we call our parent function of a quadratic. X squared, of course, are quadratic. I already have it in my head that it's going to be a parabola, so that's what I'm looking for. I'm just going to generate enough points till I see my U shape, my parabola. I'm going to start with 0. 0 squared, got it. 1 squared, 1. 2 squared, I'm going to throw in a 4. And then I feel like I can kind of see the right side of that parabola. So now I'm going to go to some negative numbers. I'm going to plug in -1 for x, careful on your sign, -1 squared, +1. -2 squared, +4. And of course, our parabola is symmetric with the y-axis there. You can see that, talking about symmetry last chapter. But that is a very important function. Our parent function, we call it, of a quadratic. When we talk about transformations, moving the graphs up, down, left, right, they generally start you with a parent function of the quadratic. So get comfortable and embrace that one. Now we've got a cubic. These kind of make kind of a loop-to-loop sort of looking graph. And cubing numbers, they can grow very fast on you, very big. So I'm going to, of course, keep it small. I'm going to start with 0, 0 cubed. I'm going to put in a 1, 1 cubed. I'm going to go to 2. 2 cubed is 8. So I'm getting close to being off the graph grid. I'm probably not going to put 3 in because 3 cubed is 27. I clearly can't fit that on the graph. Let's try some negative numbers. -1 cubed, 3 negatives make a negative. I'm going to go -2, -2 cubed, -2 times -2 times -2, -8. Let's get it plotted here. So these, like I said, kind of make what you'll see a little loop-to-loop there in the middle, a little curve. So that's your very standard parent function of a cubic function, a third degree graph. And then the next one that we're going to see come up a lot this chapter is our square root function, our parent square root function. Now we talked domains yesterday. We have to be conscientious of what numbers we use for x for our domain. You cannot square root a negative number. I can square root 0, so I'm going to start with that. Square root of 0, 0. Square root of 1, 1. Now I could put 2 in. Square root of 2 is approximately 1.4. We've seen my drawing skills. I'm going to get creative and jump up to 4 because the square root of 4 is a nice whole number, 2. So you always, for a square root function, I kind of think of it as it's half of a sideways parabola. So that is our parent function, what we call it, the parent function of a square root function. We don't have any other values in these. You're not adding 1 to x, subtracting, multiplying, anything. Just plain old boring x. That's what makes it parent functions. Now, we want to be able to graph, of course, on our graphing calculator too. So let's take a look at this guy. Use a graphing calculator to graph the function in an appropriate viewing window. Ooh, okay. Well, let's start with getting this in our y equals menu. I'm going to clear this out. X cubed minus 8x squared. Now, don't forget, your standard viewing window is the 10 by 10. Obviously, I've been using my calculator for other classes, so I'm just going to hit a quick zoom 6. Always puts you in your normal standard 10 by 10. Now, it's that third degree function. So I'm kind of looking for, a little bit of curve here, loop to loop, and it looks like, I'm going to steal the picture for a second so I can draw it. It looks like it's going to continue down here and loop through. Well, we would like to see all of that. So that's why it talks about an appropriate viewing windows. I'm going to go ahead and hit delete here and pull the graph back up. Now, couple choices on this. I'm going to show you a couple different things. You could hit zoom and then a number 3. Zoom out and just hit enter. and it's going to zoom out your screen, I still can't see the little loop-de-loop. I still don't think that's a very good picture. You could zoom out again. I'm going to get it back to my standard window, and instead of me trying to zoom out, zoom out, zoom out, I'm going to try to adjust my window. I see on the left side here, it doesn't seem like we're not seeing a whole lot on the left. So I'm going to start my window for my X minimum to -4. I kind of need -4 to the right. So I'm going to pull up my window at the top. I'm going to change X to -4. So just type over it, hit enter. And then I probably need it, I'm going to leave it at 10 for right now. I feel like we can see all of the right side. I'm still going to scale by 1. So I'm going to go down to Y minimum. It's way off the screen, this low part down here that we're trying to see. So I'm just going to I'm going to get wild and go 100. Because I feel like it's those cubed, it grows fast. I'm just going to see what it looks like. I'm going to change that also to 100. If I can't see the full curves, I'm going to come back in and I'll change these to 200. Oh, there we go. That's a nice looking picture. So let's delete this old one off. Let's get my graph back, steal this guy, and take a look at that. So now I can see this bottom piece of the curve. That's what I was looking for. So one, I'm just going to make a note on here what I used for my window. So for my X window, I went from -4 to 10. Now, there's no hard and fast rule that we all have to have the exact same windows. You just want to be able to see the curve. Maybe you did -3 to 10. You would still have a pretty good view. And then Y, of course, I did my -100 to +100. So user graphing, okay. And I'm just going to Power Technology steal it. There's my picture of the graph. And you can just sketch it. Clearly, I gave you that 10 by 10 grid on here. You can just sketch it because I really want to make sure that you can generate how to see the actual curves. So once you're done with that, though, I don't want to keep my window on -4 to 10 and -100 to 100. So I'm going to hit my zoom 6 and get it back to the 10 by 10 graph grid. Okay. And again, no perfect magical windows. Maybe you did -90 to 90. Long as you can see the whole graph is what we're after. So next up we're going to take a look at is our laundry list of many things to do here today with our graphs. How to graph piecewise functions. Remember, a piecewise function is just a function defined by 2 or more expressions. And you can see in these we've got 2, okay? So color coded, I'm going to do this one, the top one here in red. Now when I graph, I like to take it out of the function notation, the f of x, and rewrite it y equals style. And of course what's important is if x is greater than 2. So we're going to talk about that piece of it when I draw it. So first I know y equals -1 is my horizontal line. I'm going to put a dot at -1 on the y-axis. Now I'm just going to dash it on for right now because my final answer is not going to be the entire line. It's going to be a piece of it. Now for this, of course, I kind of think of that as my template. The piece of the line is only going to be where x is greater than 2. So I'm looking at my x-axis, where x is 2 right here. I'm going to go meet my line greater than, which I really feel like it's going to be hard for me to open circle on there with my smartboard. So just as a greater than, I'm going to put an open circle, and then greater than would be all the piece of the line to the right side. Because x is 4, 5, 6, 7, 8, 9, 10. Those are all greater than 2. So I only need that piece. Now, do I care if you leave the red dashes, the template on the side? No, I don't care. But power of the smartboard, I'm going to go ahead and erase it so I make it look nice and pretty for you. Here we go. Then I'm going to do the bottom one. Let's go Christmas colors and green. And I'm going to rewrite it y equals 2x minus 1. So we're in our slope-intercept form. So I'm just going to mark it out like normal. My y-intercept, -1, slope of 2. Up 2, right 1, up 2, right 1. You know I can't draw very well, so I put a lot of points on. I'm going to dash on my template as straight as I can. Now, always, we just want a piece of the line. What piece? When x is less than or equal to 2. So same thing, I'm looking where x is 2, right there on my x-axis. I'm going to meet my line. Notice it had equal to on it, so that's why I did the closed circle. I've got the big dot there. And less than is the piece to the left, because all of these x coordinates are less than 2. Now again, I don't care if you leave the dashes on your little template, that's fine. Power of the smartboard, I'm going to make it look pretty. I'm going to try to erase that. Okay. So you're doing pieces of the lines according to the constraints. All right, let's try B. So again, I'm going to rewrite f of x as y. Now quadratic, parabola. So I've got my parent function here. So I'm thinking back to this very first graph I sketched. I'm only going to have a piece of this red parabola. I'm going to start though with those points and getting it plotted. So I'm going to plot my 0, 0. 1 squared is 1. 2 squared is 4. Negative 1 squared is 1. Negative 2, 4. And I'm going to kind of dash it in, my template of the parabola. Okay. And then I only want a piece. I only want the piece where x is less than or equal to 1. So I see x is 1 right here. I'm going to go up here, 1, 1, meet my line, my curve. Less than is the piece of the parabola to the left. All of these x coordinates are less than 1. So, power of the smartboard, I'm just going to erase off my little dash template. I don't care if you do or not. But that's the only piece of the parabola that I want. Okay, final line, y equals 2x plus 1. So, of course, you're in your slope-intercept form, so I'm just doing my mx plus b, y-intercept of 1, up 2 over 1. Again, I'm going to dash it on. And we only want where x is greater than 1. So x is 1, of course, looking right here in my x-axis at 1, I'm going to go meet my line. That's going to be an open circle, and greater than, the x's are greater than on the piece of it to the right. So I'm just going to try, I won't get it all erased off, but I'm going to try to just erase the other dashes here and whatnot. I don't want to erase the dashes in the middle there, erase my blue parabola out. So when you're graphing piecewise functions, you're doing pieces of each one, and you have to look at those inequalities at the back super careful to determine which piece. All right, next thing I'm going to show you is just kind of a neat little function. It's called the greatest integer function, and the graph of it's just kind of take a look at. So when you see kind of those double brackets around x up there at the top, that of course is your indicator that you're doing greatest integer function. Now integer, remember, whole numbers, no fractions, decimals. Notice it says less than or equal to x. So just to give us some numbers, just to help us start thinking about the graph. For example, the greatest integer of 2 is 2, because 2 is less than or equal to 2. Okay, all right. Greatest integer of 2.3 is 2, because 2 is less than or equal to 2.3. Now, 1.999, I know we all want to round it up to 2, but remember it says the greatest integer less than or equal to it. So you have to go down, less than. It's going to be 1. 0.002. I need the greatest integer, whole number, less than or equal to that. Less than, of course, I got to go down to 0. Negative 3.5. Greatest integer that is less than negative 3.5 is negative 4. So you're not rounding up. You have to keep thinking less than. So when we go to graph this, it's kind of neat. It kind of looks like these little stair steps. I'm just going to t-chart it. And I'm thinking about my greatest integer function here, of course. And I'm just going to start with some nice, easy numbers. Like I'm thinking it's really you're on a range of numbers. So I'm thinking about if my x's are 0, my greatest integer for that would be 0. If I go x.5, that's going to go down to 0. 2/3 goes down to 0. 3/4 goes to 0. You get a pattern here. Once you hit 1, though, you're going to be at 1. So I'm going to say these are the x's. I'm going to put it a range from 0 to 1. Notice I got a parenthesis on that, very technical. So when x is 0 up to 1, I'm going to open circle. Gosh, that's messy. And you have a little segment in between them. Now to get the next, what I like to call a stair step. So I'm going to start with 1. 1, the greatest integer to 1 is 1. 1.2 goes to 1. 1.3 goes to 1. 1.4 goes to 1. 1.9 goes to 1. Up until you get to 2. So when I pick it up at 1, I'm going to go up here to 2, all the way over here. That's an open circle. Man, I need like a finer marker on this to get my greatest integer. I'm going to show you a better digital picture of this in a minute versus my drawing. Okay, let's try, let's do another stair step. Let's pick it up, of course, at 2. So greatest integer of 2 would be 2. 2.1 goes to 2. 2.3 goes to 2. 2.7 goes down to 2 up until you hit 3. So when I'm at 2, I'm going to, of course, go to 2 here. Everything, open circle. So you can kind of see the pattern of these little stair steps, and I just feel like I should do some negatives, of course, for you. Let's do -1. So greatest integer of -1, of course, -1. And then I think about like negative 0.2, negative, so on and so forth, up to 0. So -1, it's going to be -1. That's like solid open circle. So there's your little stair steps. So like I said, it's hard for me to draw that with my smartboard markers, but I'm going to flip ahead really quickly here and take a look at, I'm going to scroll this down. Your greatest integer function is clear at the bottom, and it's a lot better picture than what I'm drawing you here. So if you look in the bottom right-hand corner, you can see the lovely little stair steps here a whole lot nicer than what I'm drawing to you. And notice you have these open circles here, because that, of course, is where it steps up to the next level. So kind of a neat function. You probably have never seen that greatest integer function before, so I just wanted to show you that and take a look at that guy. Okay, man, my artistic skills need some serious work. Now, next thing, vertical line test. You know what? It's the same thing from 8th grade math. Use it to determine if the graph represents a function. If no vertical line intersects the graph at more than once, then it is a function. So you can see, there's really not a lot for you to write here. Just I wanted to show you some pictures, and clearly they've got some nice vertical lines drawn on them. Using the vertical lines, we see the curves in B and C represent functions. B and C pass the test. And of course, the graphs on A and D do not. And you can see why. You've got the red, of course, dashed line. It's hitting the graph more than once, not a function. Here, your vertical line's hitting it 3 times, definitely not a function. And if you draw a vertical line anywhere on the other 2 graphs, you will see it will only touch it once. You know vertical line test. All right, home stretch, my friends, and we're going to look at some pictures of graphs. Do the following equations. Define y as a function of x. So just to kind of help you, like, what the heck does that really mean on the side there? First, define y as a function of x. So the first thing we want to do is solve the equation for y. So that's the first thing I'm going to do on all 4. I'm just going to solve them for y. I'm going to add x squared over. Got it. That one, C is already solved for y. D, there is no y, so I guess I'll work on B now. So I'm going to subtract x squared, and then I'm going to square root it to cancel out squaring. Important step, make sure you put plus or minus. I know we want to maybe square root out the 4 and the x squared, but remember, you can only square root everything if you have product or quotient, not subtraction or addition. Okay, so make sure they're solved for y. Start with that. Now, test and determine if you put one value in for x, do I get exactly one answer out for y? So I'm testing. If I put any number in here for x, let's say I put -1 in there, do I get one answer out? Yeah, I get 3. If I put 0 in, yes, I get one answer out, 2. If I put 5 in there, do I get one answer out? Yes. So this is a function. The other thing I'm thinking about too, squared, parabola, quadratic. It's that U-shaped graph. You betcha a U-shaped graph will pass the vertical line test. So if you're more of a visual thinker, think about vertical line test. Okay, B right away makes me nervous because of that plus minus. Because if I put a number in here for x, let's say I put 1 in. 4 minus 1 squared. 1 squared, 1. 4 minus 1, 3. You get plus or minus the square root of 3. You get 2 answers out. I put one number in, I get 2 answers out. That breaks our rule of being a function. Plus, again, if you're more of a visual person, you could test it on the vertical line test. Its graph looks something like this. It's kind of that sideways parabola. So of course it would not pass your vertical line test. Just to put the 2 together. All right, let's test letter C. So if I put a number in for x, let's say I put 1 in. 2 times 1, yep, I get 1 answer out. 0 in. Yep, I get 1 answer out. -5 in. Yes, I will get 1 answer out. This is a function. Also, think of the graph. You're in mx plus b, slope-intercept form. You've got that diagonal line. Of course, that will also pass your vertical line test. All right, final equation, x equals 3. So of course, when we did our writing equations and lines last chapter, x equals 3, remember, is your vertical line. So you can think about that. I'm also thinking about, okay, if I put a number in for x, what are we getting out for y? Well, I'm thinking about if x is 3, if I'm making a t-chart or I'm thinking about ordered pairs, there's no y in here. You can use whatever you want for y. But like getting fancy and put 15 in there. So right away I'm like, this is a problem. If I put a number in for x3, I am getting multiple answers out. So this is not going to be a function. Or I think about, obviously it's that vertical line. Well, if I'm running the vertical line test on it, it will touch in every single point. It's not going to pass the vertical line test. Horizontal line will, vertical line will not. Okay, and then I just want to take a look at some of these graphs. We're going to start seeing some of these. I don't expect you to have these all memorized what they look like, but they're just pretty common, and you're going to start seeing these more and more throughout the chapter. Obviously, I know you know the top ones there are linear functions. We did a lot of mx plus b the last chapter, so let's just kind of move past those. Our common power functions, of course. We saw this parabola come up. You're going to see that a lot. We saw our cubic function, kind of our loop-de-loop there, and you'll see some other powers of fourth and fifth and so on. Now, your root functions, of course, relate to the power functions. Your square root of x is half of a sideways parabola. Look at your cube root and your cube functions. They're related. Of course, your fourth root is half of the fourth. Now, why are these fourth roots and square roots only half of the graphs above them? That's due to the domains. We have to restrict what you can plug in those for x under your radicals, because remember, you can't square root, fourth root, sixth root, any negative numbers. That puts you into the imaginary unit system. All right, just some other fun-filled graphs on here. Reciprocal functions, when you have those fractions, those rational functions. We saw a few of those even pop up last chapter when we were solving by graphing. We all know absolute value makes your v there in the bottom left. And then, of course, your greatest integer function, which we took a look today with my hand-drawn graph. I know it was great. Here's a nice computer-generated picture. I definitely will not judge your drawing skills on your graphs today. Hopefully you graph better than I do. Have a great, great weekend and enjoy graphing.